All right, welcome back. We are GAME3001 in the summer 2020 semester, and it's week 9, part 1 of our broadcast, and we're talking about behavior trees. So before we get there, I just want to go over the stuff that I gave you last week. So last week we talked about decision trees, and some of you might say something like, behavior trees, decision trees, what's the difference? It's a big difference. Decision trees are like, you know, you've got an input and then you make a decision. It's almost like you take that input or value, and once you enter it into the root of the decision tree, so your root node, you kind of decide whether you're going to go in one direction or another. You're going to take one action or another, and then from that action you'll have other actions that you can take. So kind of in almost like a tree-like pattern. We talked about binary trees last week and how a balanced binary tree is the best way to code a decision tree because of speed. And we also talked about other techniques. In lab, we went over how to do line of sight. So we talked about how to do line of sight with collision detection during the lab portion of our course last week. And this week we're going to do more of that kind of stuff with a bit of a lab that I'm going to get you guys to submit later on today, right? So that's something that's happening. Hey, Paul. So, you know, at the end of the day, this behavior trees is kind of like a part 2 to decision trees. Now, in the book, behavior trees comes after state machines, but we're going to handle state machines next week. We're going to talk about state machines and how they're different than both tree structures, behavior trees and decision trees, and so we'll talk about those kinds of things next week. Also last week we talked about there's 2 assignments I gave you at once. I said, here's assignment 3 and here's assignment 4, and I gave you guys due dates for all those kinds of things. And hopefully you've chosen your partner. If you're going to do it with somebody else, I recommend you do it with one other person, because the load is quite heavy for these 2 assignments. I think there's a lot of work to be done. It's not just about coding, but there's also animation, there's sound effects, there's a bunch of other things that I've asked you guys to do to create this little game project. It's like a mini game that I'm making you do, almost like one level. That has some kind of AI interaction. I also got some email from some of you saying, hey, do you mind if I do the assignment with Alex's framework? Again, it doesn't matter to me how you do it, with Alex's framework or not. I'm perfectly fine with that because his framework and my framework are very similar. He has added a couple of additional things, and if it makes it easier for you to do it with Alex's framework, I'm totally happy with that, as long as I can run it, which is important. Right, and of course you're going to demo it anyway, right? So I want to see that you guys have all that going on. So there is a video demo portion, remember, of the that you're going to have to produce for these assignments, right? So I highly recommend you create you start going as early as possible, because this stuff takes long. You got to figure that with these 2 assignments combined, they're worth 25% of your final grade, right? So you got to figure, if you balance it off and you say, okay, so if each assignment takes 1 hour per percent, that means you've got 25 hours worth of work to do max. We're talking about maximum. I try and balance it off to make it approximately an hour per percent, approximately. And this is how Alex and I formulated the assignments. So you got to figure that 25 hours worth of work is not something you can get done in a day, obviously, with any success. And even if you divide it by 2 people, it's a lot of work for someone to try and knock off very quickly. So I highly recommend you get moving on your assignment number 3. You have the basics to get going on it already. Remember, what we're asking for assignment 3 for the most part is player movement, some kind of line of sight integrated with your enemy, right? I'm looking for your own assets. Please do not use, you know, kind of assets that, you know, that I've given you. I'm also, during lab, if I have a chance to, I will try and show you a successful version, maybe not this week, but next week. I have an example of an assignment that was very successful last year that I want to show you. I'm not going to decompose it, like show you the code, but actually I'm going to show you the output. So what Herman had come up with, he's a student from last semester, and he did a very great job on it. And it covers all the bases, all the things that I asked for assignment 3 and 4. So you know, that would be like an A. What would I be looking for an A? I'll give you an example of that. And again, if I can do it by next week at the latest, I'd like to try and pull that together. So without further ado, I want to start with behavior trees and what they are, because this is what this section is all around. So the first half of the course, remember, was all around pathfinding and steering behaviors and those kind of things, right? Moving, right? How do you move your AI around? How do you find stuff? How do you search for things? That's all the pathfinding stuff and the you know, steering behaviors and all that stuff, right? That was really good stuff that you guys did in the first half. The second half is all around the AI part of the AI course, which is making decisions. How do you make decisions? How do you make an AI behave like a human or an animal? Animal intelligence, if you will. How do you do that? And what techniques what techniques are out there, you know, that have already been developed that we can tap into to make sure it's kind of the same, right? For us, for our characters. So we're talking about behavior trees, and really they're very similar to hierarchical state machines. We're going to talk about that next week. So state machines, or finite state machines, if you will, are something we're going to be talking about next week. So whereas a state, you capture, we're going to talk about how you capture the state of the game, and the state could be, as an example, you know, the entire game state. Like, where is that autonomous character, that enemy? Where do they exist in the game at that particular moment in time? What is the state of the game for all other characters, for all other obstacles? That's what state really means in many ways, especially from a board game perspective. If I have a chance later on this semester, we'll talk about board game AI and how you can use a mini-max algorithm to kind of figure that out. But basically, the difference between state or a decision, in this case, the behavior tree has something called a task. Okay, so that's what behavior trees are made of, tasks. So I have a task to do, as an example, and tasks are composed into these subtrees. You're going to notice that most behavior trees are not very deep, because you can have a series of behavior trees that do different things, and we'll talk about them, right? But they all have the same structure, and it's very similar. Notice that there's something called conditions, which is some kind of test. So this could be, again, we can use line of sight for this. You can use sensing of some kind, but something that is going to trigger the behavior. So again, it's the same kind of thing as decision trees, but there's got to be some kind of condition or trigger that triggers the action. Okay, so something like that. That's the first thing. Okay. And then, of course, we talk about different kinds of nodes. We're going to talk about both a selector and a sequence and what the difference is between those things. Okay, so I'm also going to refer you to some notes on Blackboard. So on Blackboard, I've got a few things here. One of them is an article that was written back in GDC 5, so it's quite a while ago, 15 years ago. And it's about, this one here, handling complexity in Halo 2, right? So they talk about how to do that by using behavior trees. So it's a worthwhile read for you. I'm not going to go through it with you right now, but it's a good article. It's a white paper on how they did it. And I think it's interesting. If you're interested in artificial intelligence, take a read of this stuff and see what they've done. It's always good to look at other games, and Bungie really was involved in making Halo 2 at the time, And you got to remember that Bungie now makes Destiny, and they've broken away from Microsoft, and they've broken away from everybody else, and they're on their own now, right? So and you got to, if you play Destiny or if you play Halo 2, right? One of the things about both games is not just about the mechanics of how you can move and shoot and all that kind of stuff, which is like, you know, for the most part, Halo Destiny is really improved in terms of all that. It's like butter when it comes to moving through the world, but also the AI that's being used to challenge the player and how that works. It all comes from somewhere, and I think they built up a really great foundation when they made Halo. So take a look at that. I think it's a great article to look at. The other one that might help you understand behavior trees as well is this article from Gamma Sutra that I always use when it comes to talking about behavior trees, and it goes through the details somewhat similarly to what the book does, except they break it down in a few different steps. Okay, so. And I'm going to, kind of go back to this in a second and talk about it, because what they do here is they talk about how to traverse the behavior tree and how that looks. Okay, so we'll come back to this. So that's a couple of articles that I want to talk about. And of course you have the book, right? So again, we have different composite tasks. And again, remember every when it comes to behavior, it's all around tasks. That's what it comes down to. So you have something called a selector, and you have another thing called a sequence. So a selector basically either returns with a status code of successful or not successful. Okay, that's what it's looking for. Okay, so for example, I have two options in a selector. If I have two leaf nodes, and I say, I want to be able to do a task. If the task was successful, then it returns success, and then the selector returns success back up to the calling algorithm. So either success or fail, basically, is what it looks like, right? Whereas a sequence, it returns failure if any one of its children fails, right? And it kind of looks like this. So here's a selector. So select one of these three things: attack, taunt, or stare. One of these three things, right? And let's suppose you have a sequence. The way the sequence works, and again, this is just kind of the way the book kind of outlines, when we kind of draw this stuff out. The sequence works like this. I come into the sequence itself, and the sequence has children. Here, the selector has children, but the selector selects one of them, right? Where the sequence, what it does, it says, okay, start here at the leftmost child, okay? So is the enemy visible? Yes. Go back. If it's successful, you're going to return to the sequence node, this one, with a success. So it's going to be success or fail. Return with the success. Here, selector, success or fail. Can I attack? I try and attack. If I do my successful attack, I return success or fail. Right? Do I taunt? If I'm successful, there might be some success criteria. I return back, and I can do any one of these things. There's no particular order that I can do them. Whereas here, I do them in an order. I start with here, enemy visible. If the enemy is true, it's visible. I go back to the sequence, and then I go to the next one. Then I turn away, right? As an example, and let's say I'm doing a flee sequence, as an example. So I spotted the enemy, I spotted the player, and then I run away, right? Or turn away first, turn the opposite direction, and then the next thing is I run away if I'm doing a flee sequence. But I have to go through the sequence node every single time, right? So again, enemy visible, yes. I come back to this. I report success from the enemy visible node. This is the task. Do I detect the enemy? If I'm successful, the whole sequence is still successful. Can I turn away? As an example, can I turn away, or am I stuck? If I can turn away, as an example, and I'm successful, again, my sequence node is in success state so far, right? And then I go to the next one. Can I run away? Do I run away? Am I running away? Am I reporting success? Yes, then I report success. If all 3 nodes report success, then whatever node called this sequence or this tree, I report success up the chain. But if I fail anywhere, for example, I can't turn away or I can't run away because something is stopping me. I'm blocked, as an example. There's too many characters blocking me. I can't turn away because I'm stuck. I don't see the enemy, as an example. Then this whole tree fails. The whole thing is a failure, right? Whereas here, it's not the case, right? This whole thing is the failure if any one of the tasks that are selected fail. Okay, that's a different thing. So that's the difference between a selector and a sequence, and usually we compose them together. We don't have separation here. Usually you do something that looks more like this. So here's my behavior tree. I want to move into a room. I have my selector, right? I either choose this sequence or this sequence, one of the two. How do I choose the sequence? It really depends if the door is locked or not. So if the door is locked, right, then I've got to open the door somehow. I've got to unlock it, right, as an example. So it might be this task. Otherwise, if the door is not locked, then I just move over here to this sequence. Now notice that there's kind of a similar, nodes that are here. So here, as an example, I move to this sequence. I'm saying, is the door open? Cool, move into the room. If the door is not open, as an example, right? So move to the door first, then open the door, then move into the room. Okay, that's how it works. So there's 2 different sequences that you can follow here. And by the way, this kind of move into the room thing is a classic example, right? So that's the composite. A composite is when you compose both the selector and the sequence tasks together with a bunch of leaf nodes. The leaf nodes are the actions that are going to be taken. Okay, that's what the leaf nodes are in this case. Okay, so it's a different way of making decisions. A decision tree is like, go there, if this happens, then do that, kind of thing. Here, it's not like that. It's like, hey, report success, now go do the next action, now go do the next. It's a sequence. I'm going to do one action after the other because sometimes it takes me more than one action to be successful doing some kind of behavior, whatever it is. So this is more complex behavior, and this is kind of the behavior that's been talked about inside of that little article I gave you for Halo 2. Okay. Here's a more complicated version. So again, you have a sequence. Notice the sequence is up here, and then there's a selector. So this is kind of a refactored way of doing it because here there's some duplication, right? We have move into the room, and we have move into the room. We have this node twice, and we never want to duplicate our code, so we'd want to refactor this so that it's a little bit different, and that's what the next one is done. So okay, here's a sequence. So first, in my sequence, I'm going to go to this particular selector. Which one do I do? Do I open the door? Is the door open? If the door is open, then walk through the door. Otherwise, if the door is not open, then move to the door and open the door, and then finally walk to the door, walk through the door. And that would be the next part of the sequence, which is not shown. Okay? And so you can do that kind of like this, kind of a hierarchical methodology if the door was locked. So again, here's my selector, right? Is the door open, or if the door is not open? If the door is open, take this branch of the tree. If the door is not open, then you have to go to this branch, this selector, and now you're going to go here, move to the door. The next step is, okay, now check, is the door locked or not? Kind of stuff. If the door is locked, right? Or if the door is something that you have the key for the door, let's say as an example, then you're going to go to this sequence, and this sequence says, okay, is the door locked? Then open the door, right? However, if you don't have the key, you're going to go to this sequence, barge through the door, like break the door, and then is the door open? Great. So, and then we're reporting success back up to the tree. So in this sequence, we have to have success from the selector node in order for you to move into the room. I don't know if you guys can see that, but basically the way it works is I want to go to the door, I want to open the door somehow with this subtree, and then if this subtree is successful, this whole thing reports success somehow, whether I do one or the other. That's what selector node does, either or, depending on the state of the door. Is it locked or not? If it's not locked, then I just can go through the door, right? I don't have to worry about it. I can open the door and get through. If it is locked, do I have the key? And if I have the key, then unlock it. If I don't have the key, break through it, right? Either way, can I do this? If any of these two subtrees are successful, then I can move into the room. Otherwise, this whole sequence is a failure because this is the sequence, and then it reports back failure to the selector node. So, and then whatever the calling node was from there. So I want to go through the door, and the sequence node or the selector node either reports success or failure, where this one, any one of these things can make this thing fail. So it's a different way of combining detection and making more of a complex decision using a tree structure as opposed to using a decision tree where you just go left or right. Sometimes what happens, even in a decision tree, you can get stuck or repeat things over and over again. So we have to be careful, and this is what behavior trees allow us to do. Okay, before I move on, are you with me on this? So the difference between a selector, because it's going to be on your final test, right? A selector as well as this is a selector, the question mark, as well as a sequence. A great way, and again, I think before I move on from this one, the article actually talks about this at length. So if we go back to the article here, and I just wanted to go through it, it talks about tree traversal on the behavior tree and flow. And again, I think the three states that you can get back are success, failure, or running. Okay, so running means I'm in the process of doing my sequence, as an example. Okay, so that's kind of the three states you can get back: success, failure, or I'm still running, I'm still doing, right, kind of thing. So we're also going to be talking about decorators in a second. And the only thing that's different between a decorator kind of wraps either a sequence node or a selector node. And the difference between a decorator and any other kind of node is that it only has a single leaf. Okay, it can't have more than one leaf, where a composite node can have multiple leaves, right? Multiple children. So they gave examples here. If you actually look at this, article that I've posted as well, of how to do it, right? And so if you notice the sequence, the process order is thus: sequence, walk to the door. Do I have success? Yes. If then the sequence is still running, the sequence is going to report its status as running because I'm in the middle of walking through the door, right? Then I open the door, success. If I get a success, I'm back to the sequence. The sequence is still running, right? Here's the sequence running. So you see the sequence running happens a couple times because I kind of keep going back to the sequence node while I'm going through the door. And then I walk through the door, success, right? And then back to this, the sequence is still running. And then I close the door behind me, success. And when I'm done, the sequence itself, reports back a success to the calling node, whatever that is. Okay, so that's kind of how the sequence would work. And you can do this for animation as well, right? You can do a sequence for all kinds of things, right? Here's another one. Sequence. Am I hungry? Success. Cool. I'm running. Do I have food? Success. Yes, I do. I'm running. Cool. Are enemies around? If not, that's good. Keep running. Okay, eat the food. Any one of these times, if I was if I failed the test, for example, if enemies are around, that would fail the entire sequence because I wouldn't eat when enemies are around. The entire node would fail. Okay, so that's why I like this diagram as well. Okay, and we'll talk about the inverter node. An inverter node is just a decorator that wraps. Remember, this is a decorator because it only has one child. It would wrap around the enemies around thing and invert its decision. Instead of saying no enemies around, you can invert it to make it positive. So are enemies around? Success. If I get a success, revert this to failure, right? And then report a failure back up. That's what the inverter does. It changes it. It's almost like a not sequence, right? So it changes success into failure. And why? Because it's better to have us have positive checks. Do I detect an enemy, as opposed to do I not detect an enemy? That's more difficult, right? It's a not gate, like it says here. So that is what a sequence is like. And a selector selects different options for the sequence. So that's what it does, right? So a selector node goes, there's a sequence, I walk to the door. As an example, I report success. I'm at the door, cool. I'm in running state. I go to my selector, and then now the selector has to determine what to do. The selector says, okay, so if the door is unlocked, open the door. If the door is locked, go to a new sequence. This new sequence, right? Do I have a key? If I have a key, cool, unlock the door kind of thing for the selector. If I don't have a key, don't do this sequence, go and do this one, because the selector can do one of these three things. So again, selector, is the door open? Which one am I going to choose? It's almost like a decision point or a trigger, if you will. So the door is not open. Do I have the key? No. Then smash the door, right? So I'll do one of these. And then if I'm successful with one of the things that I've selected, go back up and report success to my sequence node and then walk through the door. Did I make it through the door somehow without being blocked? Yes. Cool. Report success. Go back to and close the door behind me. If this all worked, because all of these have to work in order for me for my sequence node to produce a success, then say successful or failure, depending on one of these things. And failure could happen anywhere. For example, I have the key, I go to unlock the door, it doesn't work. It's double locked, or something happened. I'm prevented from unlocking the door. If I report failure here, then the selector reports failure, and then I'm done. Right? It doesn't go to the next thing. It doesn't go to smash the door. It just reports failure, and then I'm failed the entire sequence. Right? However, if I notice most of the times that I will be able to unlock the door, and then maybe I can open the door. But what if I'm stopped from opening the door by an attack, right? Because again, this open door is very simple. Maybe there's going to be another check in here to open the door if there's no enemies around. Are there enemies around? No. Open the door. Otherwise, fail. And then, go back up and fail the entire sequence. So that's the kind of the way selectors and sequence nodes work. And you can see this is a much more complex case where you could have a selector to say, okay, well, maybe it's better for me to go through the window, right? As an example, as opposed to walk through the door, because maybe I'm going to be more successful going through the window because I don't have a key, or the door is blocked somehow, right? So I'm going to go through the window instead, right? And it has a sequence just for getting through the window. Whether I walk to the window, is the window open, then open the window, and then climb through the window, and then close the window. So you can get through the window or the door, right? As an example. So it's kind of interesting the way this works, but it makes sense for us because we can kind of see a sequence of behavior nodes or tasks that we're going to perform, right? And the tasks are all the bottom nodes. That's the thing to notice. So example, this one, walk to the door is a task because it's a leaf node, right? Open the door is a task. Unlock the door is a task. Open the door is a task, right? Notice that there's duplication here. Open door and thing. And all we're doing is calling the same task that's been decided. So we determine the task itself by coding it. We code the task as a task object, right, as an example, and then we just point to it. That's all we're doing here. So we code it once, use multiple times potentially. Same thing with open window. There's 2 times we can open the window here as an example. So hopefully that makes sense. Again, this is for more complex behavior than using a decision tree. Okay, decision tree is like, do I see it? Yes. Okay, do this. It's pretty simple, and it's a different way of doing things. Decision trees are very commonly used, but for behavior trees can give us more complexity. And there's the game. You can actually watch the little video, Zomboid NPCs, and how they work, where they go through the door or they open the window. So there's a video attached to this thing, which I recommend you take a look at and follow. They also talk about direct decorator nodes, which we're going to talk about in a second. So let's go back to our PowerPoint. So that is this in a nutshell. I think this is a pretty good explanation of how things work on a high level. This is the theory portion. Okay. When it comes to implementation, we have to think about a task, and the task class would be our basic building block. So here, this is written in pseudocode again, and looks like either it's in Lua or it's like a version of a Pythonic kind of thing, whether it's in Lua or something else. It's very Python-like because you can see that the comments are hashtags, right? A hashtag is usually a comment for Python or Lua. So the class task in Python or Lua classes are, it ends with a colon. So this is class definition. You can see the indent in Python or Lua, in that language. Curly braces are replaced with simpler, they remove syntax. There's no semicolons, as an example. And again, I'm just assuming this is pseudocode anyway, but you can see that we have a function called run, and the arrow means returns. Whenever I talk about the pseudocode, if you're going to look at this to try and understand what it does, the arrow means returns. So the function run returns a Boolean, true, false, right? Can the task run? Is the task successful, basically, true or false, right? And that's what this task is. So the task only has a simple, the class task has a simple function, and that's what we're looking at. We run the task and see if it fails or succeeds. That's really what it is. Okay, here's the next one. Class enemy near extends, which is like the colon in C++, extends the task, superclass, right? Extends it. It's a, here, the task itself, as an example, maybe this simple task would be an abstract superclass, so a true virtual, a pure virtual, if you will, right? And here what we're doing is we're saying we're going to override the or run the run task or the run method that returns Boolean, and we're going to say it returns distance to the enemy is less than 10, and whatever that is. For example, if it's true, the distance to the enemy is less than 10, then the enemy near task succeeds. That's how the run works. However, if the enemy distance to the enemy is greater than 10, then enemy near fails, right? That's how it's true or false. Okay, so that's how it works. So it's pretty simple the way it works. You know, here it's just, you know, true or false, success or failure for all tasks, right? But the test is in the task itself. This is just the abstract superclass. We're never going to instantiate a task of type task. We're going to make it some kind of version of a child of the task class. Okay? And again, that might be confusing for some, but we'll talk about this in code. Here's another example. So to play an animation. So again, you can see play an animation is a task, but it's not the task class. It derives from task, which means we have to define a run method or function, right? So we have an animation ID as an integer, and we have a speed, which is of type float, right? Again, you can see that the types come after the definition, right? And then that equals to 1, so speed is 1. Okay, function run. So when we call this task, we call the run function of this task, play animation run, then it returns a Boolean, true or false, if my animation engine is ready. If my animation is ready, cool, then play the animation, whatever the animation based on the animation ID, at the regular speed. So the speed, let's say 60 frames per second. If I was to change this, let's say to something else, let's say my play method could also vary the animation speed, which in my case it does for my engine, the one I've kind of made with you guys, right? You can change the animation speed to whatever you want, but if I get to this point, then it returns true, and the run task is successful. This run function, which means my play animation is successful. However, if the animation engine is not ready, maybe it's already doing something. As an example, sorry, I know that I'm buffering a little bit. Then it's going to return false, and that means that I couldn't play my animation. It could also mean that my animation engine is not ready because, you know, I'm not in ready state. My player's not in ready state. There's a bunch of ways. This is a very simple way of looking at it, but it's either a success or fail. Okay. So again, here's how you make the selector task or the sequence task. This is kind of interesting to take a look at because we have our children array. All right. So our children array is an array of tasks. Notice this is the task superclass, so it could be any task that you put in here, right? And the way the selector works is it really depends on which child is going to run based on the, I'm not going to run every task here. Here it says in this particular example, for every child in the children array, I'm going to, if as an example, the child runs, if I can run the child, then return true, right? So I'm actually leaving this. So starting with the first option, I'm going to run the first one every single time and try that one in the selector. So my function run wouldn't exactly be like this, but this is just an example, right? Otherwise, return false, right? And this is more like what a sequence would be. So even though they're coded the exact same, right, as an example, the difference is in here. So for every child in the children array, right? If I can't run the task for some reason, then return false. Otherwise, return true. And that's the difference between these two things, right? So the only thing that's going to happen is I need to be able, if I can run the task, then I'm going to return false, return true, right? If I can run the task, that's the difference between a selector and a sequence. If I can't run the task, I'm going to return false here. Whereas here, if I can run the task, I'm going to return true. The default is false. The default is true. Okay, so that's the difference between the two things, selector and sequence. Okay, let me just turn this off so I don't get any more of these. From a performance perspective, it really depends on the tasks inside of it. So it talks about here, and again, you may not know big O notation at this point. I'm not sure if you've taken data structures or not, but you can see that O to the 1 is the simplest kind of straightforward performance. O to the n is a linear kind of memory task, if you will. And O log n, as an example, it depends on what you're doing. It depends on how many sequences are inside of your tree. So I'm not going to go through this too much, but this is there for you if you want to know how efficient it is. So the more sequences, as an example, then the more complex it can be. And the more depth, of course, the more depth the tree has, then the longer and more complex it can take in terms of time. So far what we've been talking about is very deterministic behavior. For example, like we said earlier up here, I can either go through the door or move to the door, depending on, if I have is the door open or not, right, as an example. So this is an example of, is the door open? Is the door not open? If the door is open, go here. If the door is open, go. If the door is not open, go here, right? And it's very deterministic. It's either one thing or the other thing. But this makes AI, like we talked about last week, very predictable, right? If I know for sure that the door is open and that the AI is going to go through the door if it's open, then I can predict when it's going to happen and I can kill the AI. Similarly, if I know if the door is closed, it's going to try and open the door or barge through, again, I'm thinking about when I hear barge through, I'm thinking about Minecraft, by the way, where the mobs try and break through the door if they can. So again, I can predict what's going to happen, and then if it's predictable AI, I can defeat the AI, right? But I think where the more interesting stuff comes along is when it's non-deterministic, where we don't have a strict order, and sometimes that can happen in, for example. Example here, in our simple example above, we absolutely have to check the door if it's open before trying to move through it, right? But if we try to move through it before we check it's open, that's kind of weird. It doesn't make sense. So the order matters here, right? The order matters in terms of how we move through it, right? And it says similarly for selectors, there's no point trying to barge through the door if it's already open, right? I mean, it doesn't make sense. So doing things in a different order, right, as an example for sequences and selectors, makes no sense. Right? However, it does make sense sometimes if we want to do something that, as an example, we want to check the door, before we see if it's, we move to the door before we know that we have the key or not, right? Kind of thing. So that's something where the AI can fail in its task or take longer to do stuff because, not all AIs do exactly what they're supposed to do, just like all people don't do exactly what they're supposed to do. They're not robots, right? So they make errors. And I think when we introduce, non-deterministic behavior to AIs, it becomes more believable, more, interesting, So, so this idea of partial order is something that we can use. right? Some parts can be strictly ordered when it needs to be, and some other parts can be in a random order. So what you could do is you can have another kind of selector, a random selector. So instead of selecting everything based on, as an example, the what tasks make sense, you can choose if all the sequences below the random selector, as an example, are equally good to run. For example, that whole window idea. Let's take a look at this one. Going back to this thing, where we had more complex set of nodes. I'm just going to go and just zoom in here just a bit more so you guys can see this better. So we have here, maybe, for example, in this case, it's equally good to go either to the door or to the window, right? I don't know which one I'm going to do. In this case, if I always did the leftmost sequence, tried this one first, as an example, then the AI would be very predictable. But here what we can do is we can just decide randomly which one to do. Go through the window or go through the door, right? As an example. And this could produce some kind of variability inside of behavior for the AI. And I think that's a good thing, right? Because it makes it more believable, right? So here's an example of a random task. So it says, okay, so here's a bunch of children in my selector. And while this is true, while I'm running, I'm going to, the child itself is going to be a random choice of the children that are inside my task list, right? So let's say I have a bunch of children, choose a random child, and then if I can run the child, return true, otherwise return false. So this is a different way of doing the selector as opposed to always doing the leftmost task or whatever. This gives us randomness, but there's a couple problems. It may try the same child more than once. So for example, maybe I try through the window, I fail, I go back and try the window again because it's just random, right? I might choose this one or this one. That's one. And the other one, it might never give up, right? If it fails here and it fails here, it just keeps bouncing back and forth and keep trying, the window or the door, regardless whether you can't smash the window or smash the door because there's a blockage somehow. Maybe something that'll make the door impregnable or the window completely blocked. So even if you do it, you can't climb through the window or you can't walk through the door for some reason. And I'll keep trying these things over and over again, right? So that's something that can happen. So a better way of doing this would be more or less to have something called a non-deterministic selector, right? Where what we do is we shuffle the tasks and you can pick one or the other as an example, but you can't pick the same task twice, almost like a unique randomness. So I pick one, but I can't pick the same one the second time. The second time I'm going to pick something else, as an example. Okay. So so here we have a couple of different kinds of non-deterministic selectors. So this is a non-deterministic selector, and this is a non-deterministic sequence. All right. So two different kinds of things. But notice it says we want to do this random shuffle. All right, and there's a couple ways of doing the random shuffle. A lot of programming languages now have a shuffle algorithm that you can do to shuffle the children inside of a list, right? So that way you only choose the children in a random order, as an example, right? So you choose the children, then what you do is you run the first child in the task. So again, for every child in the shuffled array, well, guess what? This array is going to be shuffled around, so it's not going to be the same selector you're going to choose every single time, right? And same thing for the same sequence. You're not going to choose the same order in the sequence every single time, right? And if we don't have some kind of shuffling algorithm, which is, by the way, is built into most vectors, most arrays nowadays have some kind of shuffle, especially on the Java side. I think C# you have to kind of code it on your own. C++ I think has a shuffle, but you can make your own, and you can use kind of a shuffle mechanic. Now here again, it's kind of a weird step when you look at the pseudocode, because what you're saying is, here's my original list, whatever the list is, I want to shuffle. And what I mean by shuffle is like shuffle the order. So I have, let's say, a list of A, B, C, D, and I want to shuffle the list, or I want to shuffle some cards. I have 52 cards in a deck, and I'm going to shuffle them in a random order, right? So, but I'm gonna go through each of the cards in the deck. When I pop a card off the deck, let's say Magic, I'm playing Magic. I want to, pull a card from the top of the stack. of the deck, I want that card to be random, right? But it can't be the same card anywhere else, maybe, unless in Magic I can have 4 different cards the same, as an example. But here, I want to shuffle those cards, right? So the way to do that is I take the original list and make a copy of it, and then I have a list length. So let's say, if it was as an example, I might have, if it was the card shuffling example, my list length would be 52 cards, as an example. Then, or in Magic's case, 60 cards. While my list length is greater than 1, I'm going to get a random integer that's less than this number. So from, let's say, 0 to 59, right, if it was Magic, or 0 to 51 if it was just a regular playing deck of cards. Then I'm going to decrement that number, right? So whatever that is. And I'm going to say that, and this is where Lua or Python allows you to multiply, do things in one line that it would take several lines in other languages. So for example, my list N is going to be my list K, right? So whatever N is now is going to be held by K, right? And then list K is going to be the old N. So what I'm doing is I'm swapping elements. This is an element swap. I'm taking the elements, I'm taking my list, and I'm swapping the elements around. That's what I'm doing here. And I keep doing this for the entire list. I keep swapping elements around randomly, and I might swap the same element twice, but I keep swapping elements. And this is kind of an interesting swap algorithm, right? I think it's the Fisher-Yates shuffle, if I'm not wrong, is what they're using here. And Fisher-Yates, let's see if I'm not wrong. If I remember my old computer science stuff, Fisher-Yates. Yeah, it is. Fisher-Yates shuffle is what it is. So Fisher-Yates shuffle algorithm is a classic algorithm that they use. And what it does, and here's some examples here I'm just using Wikipedia, but what it does is it shuffles in exactly the same way. It just swaps elements instead of an array. Okay? So why am I bringing that up? Because that's what is necessary to do any one of these. You want to shuffle or want to swap out the children, and you have a random. Now your list of children is in a random order, and then you're going to choose the leftmost child every single time, but it's going to be a random one. Okay, so that's how randomness can work. So here's an example of a tree with partial ordering. So I get a selector node again, and I can choose between entering the door, opening the door, or barging through the door. Which one am I going to do, right? So, and some of it is, this is a selector, but then there's going to be some sequences where here I'm in this sequence, as an example. I come through, I'm going to barge through the door, right? So either I barge through the door or I burn the door down, right? Right. So one of the two things. Am I barging through the door or burning the door down? Again, it comes from this sequence first. Which one is it going to be? Am I entering? Can I enter? Enter. Do I have to open it? Open it. Do I have to break it or burn it? Go here. Right. 3 parts of the sequence. Okay. And then this is the partial ordering part where it's random. Which one do I want to do? Barge through the door, or do I want to burn the door? Kind of thing. And then here is random as well. Notice this little squiggly is a random sequence. Which one do I want to do? Get the matches first or get the gasoline first? Does it really matter? No, but it adds in a little bit of randomness to behavior. It doesn't matter which one I get first. If I can get matches first, great. If I get gasoline first, fine. But I need to have both these components in order for this node to be successful, this sequence node, which takes me back up to this node here. As an example, I've got my elements that I can use to burn the door down. So then I douse the door and then I ignite the door. That has to happen in the right order. I can't ignite it first and then douse it. So this is where it's partial ordering. I need some part is going to be ordered in a strict way, but there's going to be some randomness in terms of the way I do things. And that, again, it creates non-deterministic behavior, which allows us to have a more believable AI, something that's more intelligent and a little bit more fun to play with, to be honest. Okay? Are you guys able to see what I'm doing? Because I've had some streaming buffering. Are you guys able to see me or no? I'm getting some plus check marks. And anyone else? Okay, good. Yeah, right now. Yeah, it's really weird. It's like I'm getting some kind of bouncy behavior. I'm not sure if it's Zoom that's causing that to happen or my internet. I mean, it's pretty crazy, right? My voice cuts. Yeah, so it could be 5 to 10 seconds. Wow, that's really long. That's a really long, cut. But that's not me. It's the internet. So but either way, you're going to get this on the video. So it's good. Hopefully the video is going to be uncluttered and uncut. So we'll see how it goes. Sorry, guys. It is what it is, right? It's the wonderfulness of the internet during these times. And I have a crazy internet, like I talked about before, where it's like 1.5 gigabits down and 900 megabits up, right? So it's not like I have a bandwidth problem. So it might be further up the line somewhere. Yeah, sorry about that. Okay, so let's keep going. It could be also my computer. That's possible, and that's why, by the way, I've been talking about swapping out my machine. I do have an update on that. I have all my parts, and I'm ready to deploy my machine. So it's the new machine is ready to go. It's just a matter of me swapping out my machine and installing all the programs and everything else I need, which is always a long process. So. Yeah, I'm pretty happy with the build, to be honest with you. It's like I said, I guess we're digressing from our lesson, but we'll talk about it a little bit at another time. But it's definitely the latest, Intel processor i9-10900K with the new LGA 1200 motherboard and so on. But anyways, we'll get to that. All right. So let's move on. All right, so decorators. So we talked about different kinds of tasks, conditions, actions, and composites, right? We talked about these kinds of things. And now there's a fourth thing that we want to talk about called decorators. And I want you to think about decorators from an object-oriented software engineering perspective. It comes from this thing called the decorator pattern, okay? Decorator pattern. And then once we start talking about decorator patterns, this is the article, by the way, on handling complexity for Halo. But when we talk about patterns, programming patterns, I'm just going to bring up design patterns. So programming design patterns, right? And there's the book that I recommend again, which is Game Design Patterns or Game Programming Patterns, which is something that I've mentioned before for you guys. It is a free book, for the most part, that is created by this guy, Robert Nystrom. And he talks about game programming patterns. If you go to the website for it, which is, if you go read now, then there's different kinds of design patterns here that he talks about. The most common design patterns that we use for games, which are kind of neat. Very, very high level, but I think it's a really good book to take a look at. But one of them, and when we talk about design patterns, think about object-oriented programming. There's people have already done a lot of the things that you're trying to do with programming. So back in the 90s, this group of four. So if I go group of four, program design patterns. If you look at that, if you search for group of four design patterns, there are a famous group of four. If you look at the Wikipedia link for it. There's a book called Design Patterns, which is Elements of Reusable Object-Oriented Software. It was written by this gang of four or group of four, and they use C++ and Smalltalk to kind of describe the patterns that are used in object-oriented programming methodologies all over the world for different kinds of software projects. And again, written in 1994, it describes different kinds of patterns, and they broke it down into what it says here: creational patterns, structural patterns, and behavioral patterns. And if you look at some of these, right? So if you scroll down to see some of this stuff, and again, I'm not going to talk about it here, but we're going to be talking about patterns throughout this course, and one of the patterns we've already talked about this year so far with you guys is the singleton design pattern, right? So if you scroll down, when it comes to creational patterns, these are the ones that are very common: abstract, factory, and so on, prototype, and singleton. We talked about the singleton this year, right, so far. And then there's another one from a structural perspective called decorator. And decorator is it basically allows behavior to be added to an individual object dynamically without affecting the behavior of other objects in the same class. And really what it is it wraps around another class so that the behavior that's added to that class is seamless. You don't know, I'm adding additional functionality to that class without modifying the original class itself. I decorate the class, in other words, with more functionality. It's an interesting pattern. And that's the pattern that is being discussed here in the book. It says we're using the decorator pattern that comes from object-oriented software engineering. It wraps another class, modifying its behavior. That's what it does. And basically, the rest of the program doesn't know if it's dealing with the original class or the decorator. Okay. So that's what it does. Remember what a decorator means for us from a behavior tree perspective. It means that it only has one, leaf node. It doesn't have more children. There's only one child that it has. Okay, so that's what it does. And the reason why is we want to modify that child. And a lot of times when we modify the child, sometimes we call the decorator, they're actually filters, right? So I want to filter the response. It's the status code. So example would be that inverter decorator, right? I want to decorate a node and I want to invert its response. So if it gives success, I want to invert it and it's going to return failure. All right, so that's a way of me decorating or modifying the response of that particular node. Okay, and you have here's an example of a limiter. So class limit extends decorator, where I want to limit how long it takes for me to run a task. So for example, let's say I only want to give a task a certain amount of time. I can wrap a decorator around that class, which basically limits how long that particular object is going to run. Okay, limit is the decorator. Okay, so what this does is it gives me a time limit for how long something is going to happen. Example would be I'm trying to break through the door. If I don't break through the door in 2 seconds, then I do something else. Right? As an example, I've put a limit on how long it takes for me to have success. If I don't kill my enemy in 3 seconds, then I run away. As an example, or I try something else. Okay, so that's the way the decorators work, right? So they modify something. You can also make something, keep doing something until failure. Again, so here's another one. So I want to keep at a task until I break down. Regardless, I'll keep doing it forever, right? Until I'm stopped from doing it. Example, I want to keep breaking down the door, keep breaking down the door, keep breaking down the door. If I broke down the door, I'm going to keep doing it. It doesn't matter how long it takes, right? Do it until failure. And you can combine these decorators along with your sequence node. So again, you can see that here's a selector, and we have a sequence here, right? So is the enemy visible? Yes. Okay, good. Next order in the sequence is, all right, so what do I do? Until fail, here's my decorator, do this one child. Remember, decorators only have one child, so it goes down to this. Here's my sequence. So this sequence has to pass, right? Whether it fails or not. So example, am I conscious? Right? Okay, good. Then hit. Cool. Then pause. Then hit again. And then if I do all of this, so I do 2 hits, let's say as an example, then this passes and I can go to the next sequence. Restrain the guy if I hit him twice, right? However, if it fails, am I conscious, or is the opponent conscious? Then hit him, as an example. If this fails, then as an example, I'm going to keep doing this. I'm going to go back down here and try it again and keep trying until this is done. Then I'll restrain the person. hit him twice. If maybe hitting twice will knock him out or stun him or whatever, then restrain him. That's one possibility from a sequence, a selector. The selector would choose either this one or this one, right? And if it's random, it could choose this one instead, right? So here's another one. Here's a selector. Selector goes to this selector. Okay, cool. Can I move? Or if I can't move, then maybe I want to, if I can hear, if I'm hearable, then creep, as an example, as opposed to, a different way of doing things. So again, this one is the key though in this sequence here, this part of the behavior tree, which is until fail, do these things over and over and over again, which is kind of a neat thing. And again, in the article that I shared with you, which is this one, Gamma Sutra article, right? So it talks about decorators in here as well, it's neat. Its take on decorators. Again, there's the inverter. All right, that's a decorator. Again, it's a filter. So whatever it gets, success becomes failure, failure becomes success. You can, create your tasks so that they have a positive way of doing things as opposed to, failure. Do I not have line of sight? Can be changed to do I have line of sight? If the enemy has line of sight, or am I being seen or not? Can someone see me or not? Right? Does no one see me? Well, then you can change that to someone see me. Yes. Well, then that's a fail, right? Because I can invert that, right? There's something called a succeeder and a repeater. We talked about this. A repeat until fail, which we just talked about, and it talks about how to do that in sequence. So again, great article. I think it allows you to understand, how to do it from a theory perspective. And I think if you combine something like this with code from the book, then I think you can be successful in getting things done for your assignment. So the assignment basically says you need to use some kind of behavior or decision. You can use decision trees, you can use behavior trees, you can use state machines. Okay, it's totally fine to use any one of these techniques in order for you to accomplish the things in your assignments 3 and 4. Okay. Here's a more complex, decorator. So again, sequence, get door stack from building. Okay, until fail, pop from stack the door. Right, sequence. Okay, inverter. So that means that it's going to invert the success or failure of this sequence. Right, you can see how complex it can get. Right, sequence, walk to the door. Okay, selector. Either do the following things: open the door, unlock the door, or smash the door. Really depends on what the state of the door is, right? Once you're completed this one, go back here, walk through the door. Cool, I'm walking through the door, go back here, here's a succeeder, right? Close the door, right? And keep doing this until it's closed, so close it. Come back out to the sequence, and then set variable. I have some kind of thing that I want to do. So the door that door is put into the, I've set it as a use door. If maybe I'm searching through in this particular example where I want to look at all the doors in a particular area. And here I've set the door to something that I've used. I've already gone through this door. I've already checked this room as an example. And it depends is if I am successful as an example, then I want to keep going through each of the doors until I'm successful. So that's kind of how it works. I think these tools give you enough to create, more complex behavior once you add in all these different things, the decorator, and so on, right? So that's kind of the first part. Sometimes we can also use decorators to guard resources, right? So for example, when we say guard resources, that means, resources are going to run out. There's a limited amount of resources that we have, right? Or maybe, you can't do something until something else is ready. I can't, harvest corn until corn has grown, right? As an example, right? Here's where you guys might be experiencing some buffering. I'm seeing the yellow sign come up, which means, hey, you might be experiencing some buffering now. That's the great thing about broadcasting live on YouTube. The buffering will be a lot of times fixed up, and you'll see a continuous YouTube stream, which is good at the end in a video. So that's what this does. It guards the ability to to use something. It says, okay, so I have a resource. It's a shared resource, let's say, or I have something that I need that there must be an order in order for me to make things work. As an example, and it could be that I need corn to grow before I harvest the corn, as an example. Maybe there's not enough of corn to go around, so I'm only going to allow you to do if I'm doing some kind of resource gathering or something, or the animation engine is already in use, as an example. So then don't play the animation engine until it's available. So if the animation engine or that component as part of my my engine's ready, then great, use it. If it's not ready, then don't try and play an animation, because something's already happening right now. Maybe it's gonna produce jitter, or maybe it's going to I've got to wait in order, in kind of a synchronous order, in order for me to use those resources, right? So there's something called, again, it's a version of the decorator that can be further described as an example in a mechanism called a semaphore. All right, so these are fancy words, but basically it's a mechanism for making sure that a limited resource is not oversubscribed. And I think I like the way that they kind of posted this in the book, oversubscribed. Think about it as I want to subscribe, or I want to get a resource. I want to get whatever I want from the game, whether it's I want to gather corn, or I want to gather gold, or I want to use an animation system, or I want to produce a sound, or whatever. And what it does is it keeps a tally of the number of resources that are available and the number of current users. So let's say, for example, I have a bunch of users, or whether the user is an autonomous agent, or whether the user is a player, okay? And I keep a tally of the number of resources that there are, and then before using the resource, a piece of code must ask the semaphore, can I get it? It's almost like making a request as opposed to automatically doing it, right? Is it available? If it's available, then the semaphore, as soon as it becomes available, is going to release that capability to the calling user. And decorators can be used for this, which is kind of an interesting pattern again. It's almost like a further way of changing decisions, right? Making decisions a little bit more complex, as an example. So again, think about this as I want to. One thing to note is that we want to make semaphores work in a thread-safe environment. And one of the challenges that we've been talking about so far, everything is running in kind of in a sequence. We're talking about in a synchronous order. And a lot of times what we want to do is run a lot of this stuff asynchronously and also concurrently with other tasks. Okay? So one of the things you're going to run into when you actually do AI in a more advanced environment is running concurrently, all right, or using concurrency is what it's called, or multi-threading, right, where we have multiple threads running different tasks, okay? And a lot of the systems that we're using, a lot of programming languages, example Java, C#, and C++, if you're programming any one of those languages, they have concurrency kind of built in. You can create a thread for C++ pretty straightforwardly. And then what you need to do is lock that thread if I'm using a particular resource. So I can lock away the ability for other resources to tap into the same resource that I'm using. Otherwise, what may happen is you might get conflicts. And so this is the idea of thread safe. We want to make it so that any request for a particular resource is thread safe. So multiple users accessing the resource at the same time, you could cause a conflict, as an example, and we don't want that to happen. So the way it works is semaphore, whatever the guard is, we're creating a guard guarding a resource. It extends the decorator pattern. So remember, decorator itself, it's got its own it extends whatever the sequence or the selector that it's looking at. So decorator is a special type of selector or a special type of sequence. And semaphore guard extends that, whatever the direct decorator is. And it can be either a semaphore for a sequence or a semaphore for a selector. Okay, that's what it works out to be. So again, the way it works is we try and acquire access to that resource. That's what we're trying to do. If the results, if we acquire access, as soon as we're done running the child's, whatever the child sequence is, then we release the lock. So when we acquire it, it's almost like we're acquiring a lock. I'm locking onto that resource. I have that thing. I'm using it. It's almost like I'm lifting the pencil. Let's suppose I want to, and whenever I think about concurrency, I'm always thinking about you and I are sitting on a desk. We both want to make a drawing, right, as an example. But there's only one pencil. And what's going to happen is only one of us can draw at the same time. When I touch the pencil, as an example, I'm going to lock that pencil. I'm going to be able to use that pencil as an example, almost like I reserve it, right? And then when I'm done drawing, I let go of the pencil, and now you can lock onto it. If I lock onto it before you do, I've locked it again, and only one of us can use it at the same time, that simple resource. When I release it, if it's unlocked, you can go and use that resource yourself. That's how kind of concurrency works in a very high level, all right? So I know it's kind of more complex and confusing at times, especially when we talk about it from such a high level, and we're looking at code examples online with actually not doing code. But the example here is that the semaphore will work in a concurrent environment, some kind of like multi-threaded environment. Okay. All right. So again, what we want to try and do is we might use a factory. And remember, we talked about different patterns. Factory is also another kind of pattern. If I go back up to design patterns, right? So structural, and then there's creational. And the creational pattern, there's something called a factory pattern. And a factory pattern is really there, right, that configures a class and calls you don't actually call the class directly. You go through the factory to configure and create the class for you, right? And a good example of a factory might be something like a monster spawner, which is actually detailed in the book, the online book up here, right, in table of contents. They talk about the idea of a monster spawner, right, as a factory. And the way that would work is that I want to spawn a monster, but the spawner it doesn't care what monster I'm spawning, right? It just cares that I'm going to spawn something, and I'm going to return out the monster spawner, or the monster into the spawner, wherever the spawner is. The only thing I have to do is configure what type of monster I want. So let's say, for example, I want a spider, right, in Minecraft. Let's suppose Minecraft can spawn multiple different kinds of creatures or mobs, right, from a spawner. So the factory itself, the factory method says, which monster do you want? A spider, some kind of zombie, do you want a creeper? Which one do you want, right? And then what will end up happening is the factory will return the object that's been created, that you've decided which one you want, right? It doesn't matter which one it is. That spawner is going to return that kind of creature depending on the configuration you put into the factory. All right. So it's almost like I'm saying to the factory, and let's use the car example as an example. I have different cars that a factory can create. The factory can create multiple types of cars, right? But they're all cars, right? Let's suppose it's a car factory. Instead of me creating, each car individually, so going to the actual car class and saying, I want a red car with, low profile wheels and all that kind of stuff, and that's my class. And then there'd be another class that's, I want a blue car. This is the class. I want a blue car with, only 3 wheels, as an example. Maybe somewhere else they have a car with 3 wheels, and they do, by the way. It's not really a car. It's like a motorcycle that has a truck-like back. I've seen those when I've gone back home, and in other places. So it really depends on how you configure the object that you want back from the factory. And so here in this example, I think I'm talking about design patterns here. We're getting a semaphore. Get semaphore is the factory, and what's happening is depending on what type of semaphore you're looking for, right? As an example, the semaphore hash table. Hash table is like a map in other languages, where it's an associative array, and the semaphore's name is what's going to contain the actual reference to the semaphore itself, and the semaphore being a decorator, right? Think about the semaphore as a guard, right? It's guarding a resource, right? So I'm saying I don't know which one I want, but I want one that is either going to be it's going to guard this resource, or it's going to guard that resource. I don't know which semaphore I want yet, but whatever the semaphore name is, I'm going to spawn that one out and return that semaphore. It doesn't matter which one. Again, a little bit difficult to understand without coding. But we just talked about concurrency and timing, and it's one part of when we make successful AI. We can't just use one behavior at a time. It doesn't make any sense, because that's what we've been talking about. Running multiple behaviors is what we need to do, right? And whether we're using behavior trees, decision trees, or state machines, we have to run multiple behaviors. But behavior trees are different in that they take time to complete all the actions inside of in the tree. For example, I want to go through the door. I want to step through a sequence. That sequence itself can take time to do, right? And so even though we're running things concurrently, so we're running things in parallel. Let's say I'm doing this sequence over here at the same time I'm doing something over here. As an example, it takes time to complete. So this idea of taking time to complete, right, makes sense. And the simplest way is if there's an action that completes instantly. As an example, a good one would be I have line of sight. Yes or no? Right? That's an action that happens right away. It completes instantly. But another action, like walking through a door or attacking an enemy, might take time to do, right? Example, attack an enemy until dead. That could be a decorator that is do until kind of decorator, right? Keep doing until you have success, right? Or it's a kind of a repeat decorator. I'm repeating my action. I keep attacking until I kill you or until I die, right? One of those kind of things. That could take time to do. And if it takes time to do, right, as an example, there might be other actions that I also want to do. For example, checking to see if there's other enemies around, right? Or some other action like taking care of my health as an autonomous enemy. Maybe that's going to take a back burner. I might sleep that action altogether until I'm done doing this other action, right? So, because otherwise what's going to happen is that you're going to have multiple conflicting behaviors happen at the same time. And what that can do is it can cause a lot of challenges. The other thing is, if you're running a separate thread for each AI, think about this now. I want to make each AI have their own thread. So they're running my AI engine, but instead of my AI engine worrying about all the players, all the autonomous characters on the board, as an example, each one of my autonomous characters has its own thread. Guys, we're going to quickly run out of threads, right? Because remember, and let me talk about how threads work just for a second. Let's suppose that my processor, I have a physical processor, and right now I'm running an i9, I think it's 8th generation. That's on my laptop. My 8th generation i9 has 6 cores. Each core has 2 threads, right? As an example. Okay, think about that for an average gaming computer, right? I have 12 threads that I can run at the same time. 12 max, right? One of those threads is definitely going to be running my operating system or something else. And I'm being very high level here. I'm actually being incorrect with what I'm saying. But let's suppose it's like this, all right? It's almost like I'm dedicating a core just to run, because the thread is like a virtual core, a processor, if you will, right? And that virtual processor, the thread, is doing some tasks, okay? For example, running my operating system. So one thread is gone just doing that. right? My host operating system, Windows, right? And there's going to be subthreads. Windows can run a bunch of these subthreads that are inside my actual thread. All right, talking about a threaded, multi-threaded environment. Okay, now I have five cores or virtual cores left. Let's say as an example, or sorry, 5 cores, 12 threads, 12 virtual threads, or 11 virtual threads left. I can do 11 more tasks in a multi-threaded environment, and that's it. If I give each of my AI a thread, right? How many AIs can I have? Not many, especially for an average system, an average gaming computer, right? They don't have a lot of it. It's not like every gaming computer is multi-threaded. And a lot of, a good example of that is a lot of programs don't make use of multiple threads. That's why a good example of architecture, we're just talking architecture for a second. If we think about the new AMD Ryzen CPUs, especially things like Threadripper, I'm not sure if you guys have done any kind of architecture or care about gaming architecture for a second. That's why this is unacceptable. But let's just pull this up for a second. So there's a couple of different architectures. You can have the Intel, but if you go with the AMD Ryzen, there's different kind of processors. If I go AMD Ryzen, AMD is a competing company with Intel. I'm just making sure you guys know this. And they have different processors that are competing with Intel's processors. And one of them is this thing called the Threadripper, all right? And the Threadripper is awesome, right, for certain tasks, right? And, you know, it has, there's a great article on this as well, on the Threadripper, and it can, you know, AMD claims that it's the best processor on the market right now for commercial use, right? You know, the AMD, Ryzen Threadripper, awesome. Because it has like 64 cores, or 32 cores, 64 threads, something like that, you know, as an example. And you're going to say, wait, that's going to run games better. That's going to run games faster, right? And we can talk about this at length. It's kind of off topic, but you're going to notice that most games, for the most part, are created single-threaded, which means no matter how many cores your AMD Threadripper is going to have, you know, there's also, by the way, something called overhead when it comes to using a multi-threaded environment, right? So you get a little bit of inefficiency when you use multiple cores. But the reality is the Intel core, the Intel processors, which have less cores and have a higher clock speed, right now, right? For example, the Intel 10th generation processors, like I talked about, right? If I go Intel 10th gen, these guys have less processors than their AMD counterparts. For example, the Core i9 10th gen, and it's way cheaper, by the way, but it only has 10 cores, like the one I'm building, right? And 20 threads, as opposed to 32 cores and 64 threads, right? But from a gaming perspective, because its clock rate is higher, and because most games are created in a single-threaded environment, they don't take advantage of multi-threading, especially from, and I'm being very high level here, guys, so forgive me, please. I'm not saying that there's no multi-threading. You have to have multi-threading, but I'm talking about truly multi-threading, using all the cores that are available, for your processor to run a game, okay? Most games don't do that. So Intel still is gaming king when it comes to, if you compare latest core, the latest processor with the latest processor from AMD, even though you have, way more cores, right? So what this means is, because multiple computers, because the average gaming computer only runs things within, much fewer cores, or much fewer threads, as an example, giving an AI its own thread is crazy, right? Because most computers can't handle it. You'll have frame rates that drop really, really low. So what you have to do is this idea of concurrency. You kind of switch between tasks, multitasking as opposed to multi-threading, right? Where I move from one task to the other, and I sleep one task while I wait for the other task to be available, and then I do that one using the same thread. Okay, so that's really interesting. So again, we can't make a behavior tree run its own thread. It takes too many resources, is what this means. And so what we do is we use a pause task, a wait task. So wait until this particular thing is ready, and then do something else. So what we can do is we can sleep for a particular duration, and then try and do that task again. Sometimes the sleep duration is almost like a limiter type task, where I want to limit how long I try and do a task before I do something else. Okay? And this kind of thing, what it does is it helps us manage behavior for our complex AI. Okay? Whew. That's a challenging way of describing things, especially when you're doing things at such a high level, right? So concurrency and timing, although we're not going to do it, and I don't expect you guys for your assignment 3 or assignment 4, I don't expect that you guys include any kind of concurrency and timing or multi-threading at all. That's not part of this. This is outside of the scope of our course, and most likely the program. All right, you won't probably get into multi-threading until you leave George Brown and go into a AAA environment. Okay, and the reason for that is because it's very complex, right? And it takes a lot of there's a lot of pain in coding something like that, and you also have to balance how many resources you allocate, and what thread safe means when it comes to creating things like singletons or statics or all kinds of other stuff that we're taking for granted in a single threaded environment. Okay, let's move on. So again, we want to run this idea of a parallel task, right? And the parallel task is going to run something alongside with a selector and a sequence. All right, and the reason why we want to try and do this is because, you know what, there's a lot of stuff going on. Your AI engine is going to run multiple, decisions all at the same time, right? And you want to go from one character to the next character, as an example, the different autonomous characters, and you're going to swap between these things. They're going to happen all at the same time, and you want to balance resources between all of them. Okay, that's what this parallel task stuff means. So again, what we can do is we can modify the task superclass to have another method. So the first one was we have a run method, okay, as an example. Again, this is all theory, guys, that we're not going to use in our assignments. But we're going to have another method that we're going to include in our an abstract superclass. It's also, as an example, a pure virtual that returns void, right? And what we're going to do is we're going to set up this terminate method, a terminate method that terminates and asks the task terminate and clean itself up, right? And the reason why we need that is because if we're doing things in parallel, sometimes we need to stop a task, or if we fail a task, we need to free up some resources, as an example, because a semaphore, which is another type of decorator, right? Remember, semaphore is a decorator is a filter. Semaphore is a different kind of decorator that guards resources. I have limited number of resources. I have an animation system. I have a, this kind of sound system. Whatever I have, I want to run at the same time. And now that I'm successful or not, I want to terminate that task if it's successful or not. And I want to clean up. I want to do that task. That's another little thing we're going to add into the abstract superclass task. Okay, that's what we're adding to enable that behavior downstream, as an example. Okay, and so here's an example. I'm not going to go through this, but here's an example of what a parallel, this task called parallel is. It's a parallel task. It extends the task superclass. Each parallel task now, it's not just a regular task. It has a bunch of children that have their own tasks, right? As an example, a task list. So each parallel task has a children list, which is an array of tasks. That's what it is, right? And what we can do is we create a list of running children, so current tasks that are active inside of my parallel task, right? So I might have each of the child tasks running at the same time, right? As an example, for this big parallel task. Think about the parallel task as a root task way up above that's governing the behavior of a particular AI, right? And what we want to do is we want to run each of those children in parallel and swap between children and give them a little bit of time, basically multitasking. Okay. So that's what these slides are. They're for your reading pleasure. right? I'm not going to go into details, and I'm not going to test you on this kind of stuff in terms of, hey, tell me what a thread is, and so on. But it talks about how to create a thread, and we're not talking about a thread like as in, threads and cores now. We're talking about a subthread. And what it does is it creates a thread for that particular child to run, and then we wait and sleep until that thread is done, and then we run the next one. Okay, and so it can look something that looks like this, where you see this symbol here means parallel task. So I have a parallel sequence, right? So these things are all running at the same time. So I have a selector, and I think this is one of the last slides that we'll talk about in any depth, but here's the selector, and the selector can do one of three things: retreat, take cover, or run this parallel sequence. All right, this parallel sequence. So that means that each of these things will run at the same time. So here's the first one. Do I have ammo? Here's the second one. Soldier 1 has, do I have ammo? Soldier 2, did they have ammo? Soldier 3, did they have ammo? So let's run all of these tasks at the same time. Okay, cool. Soldier 1, attack. Soldier 2, well, if Soldier 2 has ammo, are we in cover? Yes. Okay, well then attack. Right? So only attack, because guess what? Soldier 2 is a sniper. Soldier 1 doesn't care. Soldier 3, right? He's on. He's in ammo. He's got ammo, but you know what? Maybe what he's got to do is exit the route, right? And he's going to guard the exit. If am I close to the exit route? Well, then guard my exit. That's what he's going to do. Guard the exit while this guy takes cover and snipers you, and this one fires at you, right? So those are the three things. That can happen in parallel, which is kind of an interesting way of doing things, right? So depending on what you are, do these three things. The three different soldiers are going to do the same things. So I'm not going to go into the rest of these. Again, this is for you to take a look at. But you have this other thing called intra-task behavior, right? So you don't want to have a character finish his tasks and then just stand around or be idle, right? What you want to do is do something else, right? And so what you can do is, in the tasks themselves, while one character is waiting to do their task because the resource is taken up, get them to do something else, is what this means. And then there's another piece of code in here for called an interrupter, which is, see if the child is running, and if it is, instead of sleeping, do something else. That's what this does. I'm not going to go through the details here, but because here on these last slides, it's all about concurrency, okay? But it's good for you guys to look through this, and in combination with these slides and with the white paper that I gave you on from the Halo thing, I think it's really good information on how behavior trees work, okay? So, questions around this stuff. Again, today we've been talking about behavior trees at a very high level. When we get together in lab today, remember that I just want to mention this. We are going to do a bit of a lab. You already should know at this point how to gain line of sight. Okay, so line of sight should be working for you, and we're going to start trying to code. I'm going to start with decision trees today, and I'm going to get you guys to submit whatever you have today, right? So it's not a success failure thing. It's almost like I want you to submit your practice. If you submit your practice, anything you've come up with today, you're going to get your lab mark. Okay? If you don't submit anything, when you don't practice, you don't attend, you'll get 0. So really, if you just attend and listen and work with the code, which is what I'm hoping you'll do, you'll get your lab mark, and it'll be a pretty simple mark. Okay? So that's what my plan is for today's lab. It's really practicing the stuff that we've been talking about over the last couple of weeks, this week and last week. And that means creating more structures and making our character move, and all those kinds of things are important for us to get going. Also, other things like whatever we create in lab, whether we make a debug view or whatever, any one of those things are good things, so that way you can get well on your way. I'm trying to help you do assignment 3 and assignment 4. That's what the gist of the labs are for. All right. Yeah. So what I'm hoping that you'll do in the session, Johnny, is I want you guys to actually work with me in the lab. It'll be due tonight, though. I'm not going to make it due, or maybe I'll make it due tomorrow. But basically, what it's going to be is you can work with me in lab, code with me along, and I'll give you an extra day to get to patch everything together and submit. Okay, that's what I'm going to get you guys to do. So it won't be too crazy. I don't want to give you a lot of pressure, because I know it's like when we're coding along, especially through disconnects and everything else that you're seeing here online, it can be very challenging for you to follow me, right? So, and the other question I'm also going to get, I know this is coming, is can I use Alex's framework? And not for labs, no. I want you guys to follow my framework in the lab, right? Because for your assignment, go ahead. But for labs, we're practicing some simple things, and I want you guys to start from scratch with some of the stuff that I'm asking you to do, right? So, so for my labs, please submit my framework. It's more of an assignment framework than anything else. It's not really meant to be a game engine or anything like that. Okay, so hopefully that helps. Otherwise, guys, if you have no other questions, we'll meet back on Zoom for people who are doing Lab 1. And by the way, like I said last week, I don't care the order that you do it in. I don't care if you're in Lab 2 and you want to attend Lab 1, or if you're in Lab 1 and you want to attend Lab 2. As long as you attend and you submit your lab, it doesn't matter to me. Okay? All right. So I will leave it to you. I'm going to stop streaming right now, and then I'll see you guys, whoever's going to be there, at 12, and the rest will start at 3. So I'm going to end the stream now.